Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. Okay, this will be the last example. So far, example 5.1, 5.1 to 5.3 is all about axially loaded column. But in this case here, we are trying to look at axially loaded column with moments. But in this case, we are concentrating only on simple construction, meaning to say that the connections are pin. But at the same time, there is a moment transferred to the column. Yeah, there is a moment transferred to the column. Apart from the axial load. Okay, so let me now go through this example here. They're given here a table where the value of the NED comes from. This is value of NED. Okay, it comes from the level, comes from actually the reaction from this particular beam here, direction here, right? So here there are 3 beams connected to this top of column, beam 2, 3, this particular beam here, and there is also a beam here, beam 1, 3, and also beam 3, 3. So meaning to say that there is a value, reaction here, a reaction here, a reaction here, then the total of those would be considered to be the axial load subjected to this top column here. Similarly to level 2, there is also an axial load here, here, and here, which comes from the reaction of the beam, and from this beam, and then there will be another load there. Okay, so whatever the load is, this one from this particular arrangement, and also load from the level 2 here comes from here, that will be the total load carried by this particular column, the column, the lower column. Okay, and that's how the value of NED comes from. Okay, and let me now continue the same one. Sorry, just to give an idea. Yep, where the value comes from. Again from here. This is what I've already mentioned just now. So if this is at this floor here, so meaning to say that there is a value, in this case, right. What we have to do now is actually, based on this value here, the formula. Okay, since this is a simplified method, which is we assume this is actually based on simple construction. So we have to comply with this formula here. Now let me just go through what does this formula stand for. Right, this is NED. I did mention how to find NED just now. Let's say now we are going to design the column here, the bottom column. So the NED comes from whatever the axial load comes from the level 2 and also level 3, and also the self weight of the column. Okay, that will be the value of NED. And where this NED comes from actually comes from the reaction of the beams that is connected to the column at the level 2 and also at the level 3. So the summation of all those reaction there that will be the value transferred to here, and this one transferred here. So let's say this is F1, this is F2, and also this is the self weight. So NED will be actually the summation of F1 and F2. Now, what is MYED? That is actually the moment transferred to the column at the major axis, whereas MZED at the major axis, and this one at the minor axis. Now, how to calculate MED? So in this case here, for example, right, you want to calculate the moment at the major axis. So now, which one is major axis here? This is the major, or this one is the major, right? So this one is the major. That is Y. Nope. So sorry. Just testing you. This is Y. This is Y. Whereas this is Z. Z. Okay. So in this case here, for MYED is actually for example here, I'm taking here, let's say now that is the value. So MYED is 1, let's say now this is 147 here, that is 147, and that is the distance, is actually distance of the half of the depth, which is h over 2 plus by 100. Okay, so MYED is actually 147 multiplied by h over 2 plus 100. Okay, that will be the MYED, and the unit is in kilonewton meter. Whereas MZED, the moment subjected by the column at the minor axis, is actually let's say now in this case here, that is actually 37 kilonewton, and there is another here which is actually 28 kilonewton. So this is the Z axis. So now the value of MZED is actually 37 minus 28 multiplied by the eccentricity, and the eccentricity here is actually the that is 100, and that is, what is this, the h over 2, this is actually the b over 2, b over 2 plus 100. That is what we call MED. Okay, so that is the design effect based on axial load, moment at the y-axis, and moment at the z-axis. Now, the one at the bottom is actually the resistance. This one is the resistance. And BRD is the resistance of bending, resistance of buckling due to compression, and whereas this one is resistance of buckling due to moment at the y-axis, and this one resistance of the buckling at the z-axis. Let me go through one by one here. NBRD, to find NBRD SAD, as same as the one that example 5.1 and 5.3, is actually the minimum value of the value of this at the y-axis, and then you find the minimum value. You have to check at both axes, right? This NBRD. Again, to calculate the NBRD here, the minimum, you have to check at both axes. This is the y-axis, and this is the z-axis. Both you have to calculate the value of chi. The chi is from this formulation here is equal to 1 divided by 5 blah blah blah, and then to get the value of pi is comes from this formula here. To get the value of pi here, you need to know the value of alpha, and the value of alpha here comes from table 6.3 and 6.4, right? Comes from the ni. So you need to go to table 6.4 first, and using a row section, you have to know the limit. HOB is less or greater than 2. HOB limit, if it is greater than less than 2, then use buckling A. If it is greater, then use buckling B, right? And then you choose the value accordingly in table here. If it is B, then the alpha is 0.34. Now, next value is to find the value of lambda, and lambda is also the one that you find as in example 5.1 and 5.2, right? And then you go to calculate the value MYBRD. Again, this one, if you can remember, is almost similar to the lateral torsional buckling. You need to calculate the chi what we call chi LT, which comes from this formulation here. And to get the value of chi here, you need to know this formula here. Then to get the value of pi LT, you need to know the lambda LT. Now the lambda LT here comes from table 6. I forgot already which table. You got the value there, and then from here you get the value of now you need to value MCR, right? MCR, because you need to find the value MCR from here first before getting the alpha LT. You need to value MCR. MCR comes from this formula, and then you go back, you get the value of pi and also the value of chi, and then you get the value of MYBRD. For the case of MZBRD, is just use this formula here, the Fy WPL Z over lambda, which is 1. So once you have got all this value, then check whether it is less or greater than 1. If it is less than 1, then okay, then I'll go back to the example. I'll go back to the example here. This is where I mentioned just now, summation from the load from the top column, from the level 3 and level 2, and then this is how you find the value of MYED. Okay, I did mention the H over 2, and then you also calculate the value of MZED. In this case here, for this particular example, right, MZED is 0. Why it is 0? Because why it is 0? There is no moment at that particular axis, so MZED is 0. Okay, so again the same step as before. That is step 1, section classification. Step 2, checking the cross-section resistance, and the step 3, the one is a bit long, is actually the checking the buckling resistance. Okay. Okay, I already mentioned here how to find this one, and then MYBRD to get the chi value here. to get that chi value, you need to know to get the chi value here, you need to get this phi. That phi here comes from here, that value there, phi. Oh, sorry. This is for lambda chi LT. So it's just matter of just picking up the value here and just put into the respective value. This is lambda LT here, which is that value there, which is equal to this one. And then you know MCR from here, from here, and then you will get the value of MYBRD. So again, once you have got all the value, this is the value that I mentioned just now, plug into this here, and it's less than 0.1, it's less than 1.0, so the section is adequate. Right, thank you.